That's why. Even the Nobel Prize winner, Richard Feynman, even that guy cannot explain the energy term. Once he raised in his class and he told everyone that we cannot define what is energy. What we do know is what energy does. And what energy does? Yeah, so energy is the ability of doing work. The ability of doing work. If you are contained with more amount of energy, you have the more ability of doing work. In physics, work and energy, they are assumed to be analogous to each other. Okay, they can be worked as a replacement to each other. Energy and work stands for one. They are similar, conceptually different, but mathematically similar. All right. So we have defined energy. Also, okay, so in every physical quantity in physics has a type. So energy is a scalar quantity, only has a value. Okay, no magnitude. The symbol of energy is capital E. It's the symbol, and the units of energy, the SI unit, the standard unit of energy will be joules, represented by capital J. And if you are writing the spelling, then write in the smaller letters, joules. For example, if I'm containing 1000 joules, so 1000 joules like this, or you can write the spelling but with the smaller letters. That is the symbol of joule, capital J, and the energy symbol is capital E. So energy is the ability or capacity to do work. That means it is the ability to make something happen. What can happen? Yeah. Energy can move things. Okay, the effects of energy. Effects of energy. Energy can move things, to move objects. Using energy, what you can do? You can move things. What else? You can heat up something. You can raise the temperature of a body. For example, if you rub your hands, you're moving also. At the same time, you are generating heat between your hands. Okay, what else you can do? Energy can create sound. So when there happens a volcanic eruption, it occurs with a sound. When there happens a massive earthquake, okay, then there is a massive sound. If you have ever encountered an earthquake, you must have heard a sound also. If you're at the epicenter, it's a kind of blasting sound. You may feel like there is a blast happen if you're at the epicenter. Okay. So energy generates sound also. What else? Energy can give off light. Matchstick, when you're lighting up a candle, that is an example of when energy, the heat energy is getting us light. So energy can produce light also. Okay, these are the following effects. Okay. The stretching, energy can change the shape and all. It all comes in the moving part. Okay, these are the basic four things, the fundamental changes that energy can bring to object. Yeah. You remember that story of James Watt? James, yeah, you told me about this. Yeah, the James Prescott, okay, not Watt, it was James Prescott Joules. The unit of energy is named upon his surname, James Joules. He was the first guy who noticed about this, and in his honor, the unit is regarded on his name, joules. Okay, what was the story? That he went on a trip with his family, okay, in some waterfalls, and he observed that the water coming at the bottom from the fall is a bit heated up, and the water at the top of the fall was a bit cool. So temperature is changing for the same fall. Why is it happening? So while falling down, okay, due to the kinetic energy, the energy is increasing, the kinetic energy, the energy of motion, because the water is moving. So whatever energy was contained in the motion of water is now, since water has settled down on the bottom, there is no motion now. So this energy will be stored in form of heat. This is why the water at the bottom surface is a bit heated up. Okay, this was his observation which led the foundation of further studies in energy, and this is why we regard him by making the unit of energy on his name, joules. Okay. Yeah. Now joules is a standard unit, the SI unit. Okay. When I'm saying standard unit, so SI units, if you don't know, so SI unit, it is stands for System International. It's a French term. This is why we call it SI. Otherwise, it's IS. In English, it is IS. But we are habitual of saying SI unit in physics and science. So call it SI unit only, but it stands for, in English, International System of Units. I comes first. But since you're talking about in French, System Internationally, so it's SI. Anyways, so SI unit is joules, but there are other units also. For example, in India, on the packaged food, when you see the wrapper of the food, the energy is mentioned in calories, kilocalories. Okay. In Australia, the energy remains on the food wrappers as joules only. Okay. The multiple units can be there. For example, microjoules. This is a sign of micro. Microjoule stands for 10 to the power minus 6 joules. Millijoules stands for 10 to the power minus 3 joules. Kilojoules stands for 10 to the power plus 3 joules. Okay, there can be multiple units. For example, megajoules, capital MJ. Megajoules stands for 10 to the power plus 6 joules. 6, yeah. Gigajoules, so giga stands for capital G. Gigajoules will give us 10 to the power 9 joules. Okay. When I say picojoules and all, so they will be having a 12 order. I'm not sure about positive or negative. So pico stands for 12. Like mega stands for 6, giga stands for 9. The order remains same. Okay. Anyways, I was talking about the calorie. Calorie is also a unit that we see for energy over the food packages mainly. In India at least. 1 calorie stands for 4.18 joules. Okay, 4.18 joules. And for your reference, so a McD burger it contains usually 540 joules of energy. Okay, 540 calories. Okay, 540 calories it will give us. On a usual basis, a healthy guy should consume, I think, 2500 kilocalories. Okay. So 500 comes out from McD burgers. If you eat 5 burgers, you're done for the day, ideally. Okay. Do you count calories or observe when you are having your meal?
No, not that much.
All right. So like when I'm having my thali, like the meal, I observe like in a single glimpse how many calories it can be, roughly. Like a chapati barely contains, I think, 10-20 joules of energy. So if you are having 4 chapatis, you are having 50-80 joules mainly. Anyways, do you have chapatis or what do you eat usually?
Paratha. Maybe just it.
Say it again.
Paratha.
Okay. Like the Indian meals only, or like it's a bit changed?
No, it's just Indian.
Okay. Okay, for your reference, it was about food, the burger thing, but I can give you a more relatable analogy. Your McD burger, which was 540 calories, which was equal to, in your Australia and France, it will be, I think, something 2200 kilojoules, because a single calorie contains 4.18 joules. So you can multiply them and you will get a roughly number of 2200 kilojoules. This much of energy, a single burger. And for your interest, I'll tell you that this much of energy is produced by a LED light bulb for 60 hours. A LED bulb produces this much of energy. Okay, not produces, it utilizes this much of energy. If it is running for 60 hours, 60 hours will be 2.5 days. Okay, so for 2.5 days, this much of energy consumed via LED single bulb that you single-handedly consume in a burger meal. Not in a meal, in a single burger. Okay. Now comes on the effect of energy quickly. So effect of energies can be, we have already seen, it can move and it can lift also. Using energy, you can lift objects. If you're not energetic, you won't be able to move, you won't be able to lift. You can stretch objects. So somehow you can change the shape of also. Stretching, change the shape. If you're having a rubber toy, they're stretching it, you're changing the shape. Or you can compress also. There are smiley balls, so you can compress them. You will change the shape of the smiles. Also, what you can do with the energy, you can heat up objects. You can heat up objects. Energy can be used, the fuel, energy that we are having, the petroleum and all, they're all heating up. They're bringing the effect of heat. They're bringing the effect of motion, lifting, stretching, light. Okay. So these are the ways of energy. These are the phases of energy that you can see. Okay. Energy can drive a chemical reaction. A chemical reaction is also only possible in the energy presence, or a nuclear reaction. And push electric charges. When you are seeing charges are flowing in a wire, that means current is flowing. So in order to flow the current, you require energy again. And for that requirement, you add cells, batteries in the circuit. Only then your current is possible and flowing. Okay. So the question can be formed from this topic is changing the units. For example, they can tell us a chocolate bar is listed with the energy 950 kilojoules. For a chocolate bar, it's understandable also. This much of energy a chocolate bar can consist. They're asking how many joules are there, converted into joules, kilojoules to joules. So question can be formed on changing of units. This kind of question is over. You can write like type. So type 1 problems can be on change of units. Change of units. So how will you do it? You know that, yep. So a single kilojoules, 1 kilojoule contains 1000 joules, and finally your answer is this much of joules are there. Okay, if they are asking you to write in the standard form, that is in the order of 10, this is how we do it. So add a decimal point hypothetically after 9. And how many digits are after 9? 1, 2, 3, 4, 5. So write like only this, and 2 into the power 5 joules. This is how we write in the standard form. The standard form means you have to write only with the significant figure. The 0 are on the, they are in the significant figures here, but not in the standard form. You have removed all the zeros. Then you add a decimal point just after the first number. You have to add a decimal point just after the first number. Only 1 digit is allowed on the ones place. There can be no 1 here, no 2 here. Okay. Only 1 digit is allowed before a decimal point. So you have a decimal point here, and all the digits have to be moved beyond it. In order to move it, you have to add 10 to the power 5 here. Okay. Anyways, the conversion can be from calories to joules also. You know the conversion. Remember the conversion. 1 calorie equals 4.18 joules. Were you aware about calories or only joules? Okay, it's a good thing then. Okay, so there is a question that people may ask you, and such kind of question is also asked. I think your board, your school curriculum is more like asking conceptual question rather than the numericals, right? So I told you earlier also, they can ask you, why is it acceptable for a scientist or a physicist to define energy by what it does rather than what it is? Why we are not defining energy what it is? Even though we don't know, why we're not even trying to study? Why we are just feeling sufficient to know that what energy does. Why we're not digging more into what energy is? Because the reason is, as long as we can measure energy in standard unit in physics, okay, as long as we can measure the physical quantity in units and we can predict how it changes form, and we can build the instrument using the physical quantity, it is sufficient for us. At least in science it works. It is workable as long as we can measure the quantity like energy or other quantities. As long as we can see how is it working, we can see how energy is working, how energy is transferring or transforming. As long as we can create instruments working on the principle of energy. Yes, we have created the engines which is working on the principle of energy. We have created power plants which are working on the principle of energy. So it is sufficient for us. All the three principles of sciences are working. We can count it. It is measurable. We can see how is it working, and we have created instruments on it. So we don't need, what else is left? Everything is contained. Okay, it is workable for us. We are not, even people are trying to define energy in more rational words. We have defined it, but in more quantum terms that we will see in our graduation if you continue with physics. Anyways.
Yeah.
Then we saw the forms of energy. If you remember, we are having briefly two forms only. Forms of energy. First is kinetic energy. Kinetic energy. Second was potential energy. Potential energy. See, only two categorizations are there for energy on the fundamental basis. Two categorization of energy, because we got energy of multiple kinds: light energy, nuclear energy, kinetic energy, potential energy, elastic potential energy, gravitational energy, energies of multiple, chemical energy, energies of multiple kind we are having. So we have to categorize them all, so that categorization help us to study them better. This is why we categorize things. Okay. So now the question is, what is kinetic energy? Kinetic energy is the energy of motion. If anything is moving, it is due to the kinetic energy stored in it. Again, we are defining what kinetic energy does. So kinetic energy enables the object or the body to move. That's all. It is the energy of motion. Energy of motion. That's it. If anything in your sight is moving, it is because of the kinetic energy it contains. What about potential? So I will define potential energy, but before that, every energy other than kinetic energy is potential energy. Which is non-kinetic is potential. All the energies. There is no further categorization is kinetic, but there are further categorization in potential. What is potential? Potential energy is due to their position. Energy due to position. So if there is a paratrooper, who is paratrooper? The person who jumps from helicopters or planes high in the sky from a height. Okay, they are paratroopers. So there is a paratrooper who jumps from 10 kilometer high, and there is a paratrooper who jumps only 1 kilometer high. Who will collapse to the ground more aggressively, the 10 kilometer one or 1 kilometer one? Obviously 10 kilometer one. Why is it so? He may rupture also as he hit the ground. So why I am saying so? Because more the height, because of the position, he was higher. Higher is a kind of position also. He was not higher. That means it is also a position. Not being high is also a position. So someone is falling with a greater aggression. Someone is falling fine. Okay. So it was containing, the 10 kilometer was one containing more amount of energy. The 1 kilometer guy was containing less amount of energy. The energy was changed due to the motion. As you go high, as your height rises, potential energy rises. But this is not the only definition of potential energy, only example of potential energy, not the only way of understanding potential energy, because potential energy has multiple phases, unlike kinetic. Kinetic has only one phase. That's it. But in potential, we got further subdivisions. For potential energy, we are having gravitational potential energy. First of all, the one which I have given an example for, gravitational potential energy. In short, I call it GPE. G stands for gravitational. Due to the gravitational field of Earth, it arises. Potential energy, gravitational potential energy, it is due to the height of the objects. Not specifically position. Now I'm giving a word to a position, which is height. Due to the height of the object, it's GPE. There are the formulas of GPE that we may see further in the lecture. GPE, after gravitational potential energy, we are having elastic potential energy. So when you stretch a rubber band, so in the stretched position, okay, when it is already stretched, what happens when you release it? It suddenly regains its shape. So in regaining its shape, where does the energy coming from? Because when you stretched it, due to the stretched position, some energy got stored into it. This is the elastic potential energy which got stored into the stretched band. Due to the stretching position, elastic potential energy it is, which further will be utilized in regaining its shape the moment you release it. Elastic potential energy. Okay. Then we got chemical potential energy, the one which is stored in your cells, the batteries. This is chemical potential energy. It is stored in the chemical bonds. As the chemical bonds break, energy releases. I'll give you a very simple example of NaCl. NaCl is not stored in your cell, it's a different thing, but I'm telling you how it works. So NaCl is a very strong, very stable bond in chemistry. As it breaks into Na and Cl differently, it releases enormous amount of energy, which further will be used. This is why I'm saying energy is stored in the bonds. It is chemical energy. As you break the bond, you may get the energy. So your cell, your batteries contain some kind of chemicals, like your mobile phone batteries also contain lithium-ion batteries these days. And okay, so there is a new discovery which is happening. The paper batteries. Okay, they are reducing the thickness of the batteries. They are making it more thinner. So because they are having more efficient chemicals. As of days, lithium-ion batteries are more efficient. Now the people in China, they are working for nuclear batteries. Okay, they are planning to build some nuclear batteries. Your mobile phone will contain nuclear batteries, though it is very risky. Okay, but they are working for it. If it is worked, see, electricity was also risky when it was discovered, but we have managed to work it through our life. In the same way, these people are working to make the nuclear energy safer. If it works, then once you buy your mobile phone, you don't have to charge your mobile phone for next 1,000 years. Okay, such efficient is a nuclear energy. Nuclear fuel is very efficient, the most efficient fuel that we are having till today. Anyways, we talked about the chemical energy. After chemical energy, we are having the nuclear energy, the one I have just explained. Nuclear energy. In chemical energy, we were breaking the bonds. In nuclear energy, we break the atom, not even atoms. In atoms, there is a nucleus at the center. In the nucleus, there are neutrons and protons inside the nucleus. We break the neutrons. Can you imagine? Okay, we are not even breaking the atoms, we are breaking the. So it's not like that we are breaking a biscuit, like a piece of cake. No. Okay, it's neutrons, it's a subatomic particles, very small. So using quantum mechanics principles, we can do it. What we do is, the rays do it, we don't do it. What we do, like a laser light, it's more, we incident some lights on it, some kind of rays, some very heavy rays. These rays break the neutrons. Again, neutron is not a particle. Neutron is something not like solid. We don't know what neutron is. Is neutron solid or is it only energy? But whatever it is, we are able to break it. And once it is broken down, nuclear energy releases. Okay. Last potential energy was magnetic energy. Magnetic potential energy, it is stored in the magnetic field of magnets. So you have seen magnets, and we can feel when you bring a magnet in the contact of the other and you're not freeing it, it is still in your hands, you can feel some force. It can be repulsion or attraction, but whatever force it is due to the And where there is a force, there is energy also. Okay. So this energy is stored due to the magnetic field surrounding that you are in. Okay. Okay, we can further discuss, for example, the kinetic energy. I told you kinetic energy is only kinetic energy. But if you want, you can further divide kinetic energy into forms. For example, your electric current, electricity. So it is also kind of kinetic energy, electricity. Why? Because charges are in motion inside the wire. So where there is something due to the motion, it is the kinetic energy. So electric current is also containing kinetic energy. The thermal energy, heat energy. So when you heat water, you can see the water particles are in create motion. They are vibrating. So heat energy is also a kind of kinetic energy. Sound energy is also kinetic. Okay, how do we hear the sound? Because it is a physical form of energy. Sound is more physical. Why? Because air particles are vibrating. They are colliding with each other. When I say something, the air in my buccal cord, okay, it is carrying the specific vibrations, which is further colliding with the air particles and then colliding to the air of your ears, and then particular this air, the vibrating air, okay, which is synced with my voice, is now colliding with your eardrums, beating like a drum in your ear, and then our brain can understand the beating of the eardrum. This is how it works. Okay. So how question can be formed on this particular forms of energy concept? They may tell us a burning candle has at least 4 forms of energy. What are these forms? A candle is burning. A burning candle. What energy a burning candle has? So first of all, it is burning. It contains heat energy. First of all, heat energy. Second energy can be in a burning candle, chemical energy, because the wax is melting. The wax of the candle contains chemical bonds. Chemical bonds are breaking. This is why it is melting. So chemical energy also is there. Then we can see the light also in the burning candle. So light energy is also there. And somehow you can hear a hissing kind of sound. Sound energy may also be there. Okay. For example, they may ask us a microwave heating a soup. What energies are involved? So when a microwave is heating a soup, electrical energy, first of all, a microwave requires electrical energy. Second thing, heat energy, again, microwave heats, so heat energy. Then in microwave, we got electromagnetic disk, which creates the electromagnetic kinds of form, which further heats the object. Thermal energy is there, light energy is there, and then sound energy also, because microwave contains sound. You noticed. Okay. The next thing is energy transfer and transformation. If you remember, energy transfer and transformation.
Yeah.
So there are different things, transfer and transformation. See, transformation, the energy will stand for change, for means kind, type, and transfer is simply changing. So energy transfer is when energy moves from one object to another. Single form of energy is being transferred. Energy is not changing its form. For example, only one form of energy is moving from one object to another object. That's it. That is a transfer. Okay. If you are moving from your room to your study, so you are transferring from your room to your study. This is the transfer, because you are you only. You are not changing your form. Okay. So one form of energy. If heat energy is there, if heat is being transferred from me to someone else, this is transfer. Transformation is different. Transformation means, yeah, energy is changing its form. When energy change from one form to another form, it may reside into one body only, to one object only. but the form is changing in transformation. So transformation changes form, transfer changes the position or the location. In transfer, location changes. In transformation, form is changing. Form what? Energy form, light energy, electrical energy, sound energy. These are the forms. Okay. So when a hot frying pan heats up the cold veggies, so heat is being transferred from the pan, the heated pan, to the cold veggies, and then the veggies are getting heated up. It's transfer of energy, because only heat energy, one form of energy, heat only is being transferred from pan to the veggies. But in transformation, a solar panel turns light energy into electrical energy. So in the solar panel, the transformation is happening in the single body of transfer of solar panel. Light energy is changing into electrical energy.
Yeah.
Okay. Now there are 4 ways in which energy can be transferred. Say it again.
No.
Okay, there are 4 ways in which energy can be transferred. I'm talking about transfer now in a bit detail. 4 ways. What are these ways? Mechanical work. Because when you have to transfer energy, you have to do some work. Okay, if I say study, that means you have eaten up your food, you have fueled up your body, and now you will be exhausted after studying for 2 hours. This means that by working, you have exhausted your energy, you have transferred your energy into something. So working is a mean, work is a way of transference of energy. This is also a definition of work. Work is a way, it's like a vehicle, it's like a medium, right, which enables us to transfer energy. Without doing work, you will not be able to like transfer energy. You have to do some work. So mechanical work is a way of transferring of energy. What is mechanical work? That means you have to apply some force on object.
Yeah.
Okay, force. Like pushing a trolley. Okay. And then second thing is heating. Heating is also a way of transference of energy. Transference. So when you heat up your pan, so whatever stuffs are there in the pan, they will also get heated up. So energy is being transferred from the pan to the stuffs in the pan. Okay. Heating can be done in 3 ways. I'll just give you a brief information about that. Conduction, convection, and radiation. Conduction happens when the objects are in touch, like the pan and the veggies. That is conduction.
Yeah.
Radiation, when heat energy is transferred in the form of waves.
Radiation.
Radiation,
Oh,
okay, when it happens in the form of waves, as in your microwave. What happens in your microwave? There is no heating element, nothing is being heated up. Okay, microwaves are there. For example, your infrared cooker, cooktop, not cooker, cooktop, the induction cooktop. Have you heard about it?
no.
The electric cooktop, the slab, the electric cooktop, it's rectangular in shape. Okay, you plug in the fire. I got one, but I'll wait. See, this one. Have you seen this? See, so we just
It's
keep
not like
it.
a stove.
So it's not a stove. There is no gas or anything required for it. Okay, so it's a plug. You just plug in, and then this part. Okay, this part will be heated up, and you just keep your vessel onto it.
Oh, I think I have that. But okay, or something.
Yeah. So what happens is, it is due to the radiation. It creates waves, infrared waves, and these infrared
How do
waves
they create the radiation?
are radiation.
But then how do they create in the microwave? Like,
So they are having the electromagnetic discs, some kind of disc. When electric current pass into these discs, they create waves of higher frequency.
oh,
Okay, and
How do you
this,
control the temperature?
so higher the frequency, I'm not sure about the frequency of wavelength, but higher any of that on raising the electric current, it will be more heated up.
Oh,
So the microwave and the infrared wave both are acceptable for heating objects. Now if I move to further rays, like beyond microwave and this infrared, there is gamma rays on the top, which is lethal, which is such lethal, okay, which comes from the sun. This is why
yeah.
we apply the sunscreens and all to protect us. It is such impacting that can cause cancer in our skin. Okay, this is one thing. We're talking about the heat. So I told you the waves of heating: conduction by making a contact between the objects; radiation, for that you don't require a contact, or you may need it. Okay, but waves are there. As long as waves can pass through it, the object, it will be heated up. Then the second was convection. Convection, for example, you are sitting in a, what happens in sauna, like when you are sitting, it's a room where steams are created, so the air is quite heated up. If you are in there, you will feel the heat without any contact. So without contact is convection. Then waves is itself a way of transference of energy. For example, you're talking over a radio, or you're talking over the mobile phones. So waves are traveling from one place to another. Energy is being transferred, and this energy is causing us to hear each other. Fourth way is electricity. Electricity is also a way of transference of energy. So charges flow through a wire. It is carrying energy. See, from the power station, energy is reaching to your house due to in the form of electricity. Okay. Now the most important thing in this particular topic is the energy flow diagram. How the energy is flowing. Energy flow diagram. It's very simple. Energy flow diagram. They may ask us to draw the energy flow diagram. We just have to show with the use of arrow how the energy is being flowing. For example, in a torch, how the energy flows. So what is the source energy? First of all, we will write. So we will draw a box. In the box, we write the source energy. Source energy in the torch is battery. Okay, you will write battery. Battery in the brackets, you write battery. In brackets, write the location and what kind of energy is there? Chemical. Then again, you will draw arrow. This energy is being changed into what? Into electrical energy. Electrical. And in brackets, you will write wires. The location is written in the brackets. Then the electrical energy is further changing into light energy. Where? In the bulb of the torch. In the bulb, it is changing into heat, into light energy. Thermal, see, the purpose of torch is to lighten up. So if you have reached to the purpose, there is no requirement. Otherwise, you can also draw it like this. From electrical only, when enough sufficient current flows in the wires get heated up for a longer time. So the same source, electrical energy, is converting second box. Heat. Heat in where? Heat in the bulb, heat in the wires. You can write it. Anyways. So this is how we can draw the energy flow diagrams, how the energy is being flowing. We will draw the boxes. The first box will be of the source. The last box is of the purpose. If you have reached your purpose, you are done. For example, for photosynthesis, for the photosynthesis process, what will be the energy flow diagram? So light energy is the source energy. And where is it? It's coming from the sun. Sun is the source. In the process of photosynthesis, where plants create their own food by using the light energy. This energy is transferred into what? Into chemical energy, because plants needs energy. This is chemical energy, glucose. Where it happens? In the leaf. If you remember, I told you a story about how the microwave oven was discovered. So in Second World War in 1945. Okay, there was a
We saw like some.
yep, there was an American engineer by the name Percy Spencer. Okay, American engineer at the time of Second World War. They were creating enormous patents of that time, enormous invention during the World Wars. So they have created a microwave radiation, which was used in the World War radars. Okay, because in World War II there were planes, they were using the radars. So in the radar system, they were having a microwave producer, a generator of microwave. The engineer Spencer was standing around
It's
the
just some
yeah.
radiation thing. And then he's talking about.
Yeah, so the microwave generator created some radiation. He didn't know about the radiation. He was only standing. He was the engineer. He was only observing the radars, locations and all. And then there was a small, I think, chocolate in his pocket. And at the end of the day, when he was exhausted and he finds the chocolate in his pocket, and he found the chocolate was quite melted, quite messy. So everyone, like a normal guy, will get annoyed to see that after an exhausting day. But his observation was good. He didn't get annoyed. He observed it. The why it happened, because he was standing right side of the microwave generator. So he thought that microwave generator is heating up, melting up my chocolate. Then he immediately brought popcorn,
Yeah.
and then popcorn kernels also popped out. And for his surprise, when
How do you realize it's that?
he realizes something is happening, something is raising the temperature. If chocolate only melts when the temperature is risen, a solid thing only melts when there is temperature rise. Okay, so
I know, but then like hasn't chocolate ever been in your thing and then it just melts?
because he was in the contact of the radiation, because waves flow in all directions. Okay, waves flows in all directions. So it flows into his pocket also. It flows, the microwave flows into the chocolate also, and hence it melts. Though it the process, the waves were very slow. The person didn't feel it, but it happened for the whole day. So it was impactful enough. Then he raised the microwave frequency and brought the popcorn kernels, and then they popped out. He was very sure then. His colleagues are also surprised. Then he brought some egg, and the egg quite busted on his colleague's face. Then he got to know that we can
So then
create.
how did they find out?
So they found out
How
that
did they
yeah.
find out that you should put that?
So then they create.
How did they find out that you should put that?
You shouldn't what? You shouldn't put metals into it.
Oh, okay. Yeah, that.
Yeah, so it was quite an observation. Why is it happening? Why it won't work? It's a different thing. What I'm saying is, then he created a first microwave in your late 90s. First microwave oven of that time. It was as big as of a refrigerator today and as expensive as a small car. Okay, so it was quite expensive of that time. The first microwave oven. Anyways, now comes the concept of useful versus wasted amount of energy. Useful versus wasted. And when we were clear about the wasted and useful concept, then we will be knowing the efficiency thing also. Anyways, what is useful versus wasted comparison? So in real life, energy transformation that is happening are never perfect. For example, what will you expect? You will expect ideally, if you are having 10 joules of energy and you want it to transfer exactly straight up transferring into 10 joules of heat energy, you want it to transfer into 10 joules of electrical energy, for example. But the transformation is not perfect. What happens is it only transfers into maybe 8 joules of electric energy. The 2 joules are wastage. Right? This was input. Or you may say useful energy. Okay, input. This was input. And this was output. You want the output as electric. Input was heat. You want to convert all the 10 joules of energy into exactly electrical. It doesn't happen. some energy gets wasted also. This is the wastage of energy, wasted amount of energy. And 8 joule is the useful energy. Clear? So you were having 10 joules energy. So input is your total amount of energy. Output gets divided into two parts, useful and wasted. The wastage can be anything. Okay, it may also radiate into the air, it may go as sound also. Wastage is anything that we don't want. If you are only wanting electric energy, so any other effect that you are seeing is the wastage. Okay, useful energy is always lesser than total energy, always. You can never make a perfect device, perfect instrument where energy transformation happens. Ideally it doesn't happen. Your input will never be equal to output always. Some energy gets wasted. Let's talk about the energy efficiency now. So efficiency will tell you how wasteful is your instrument, how wasteful is your device. A device will be, say it again. That's what I'm saying. The amount of energy, right? So amount of energy can be measured using different ways. There are formulas for energy, I told you.
Yeah.
Okay, the formulas for energy is force times displacement. I'm not going into that. I'm just telling you, don't get confused about it. I'm just saying energy has formulas. As long as you get the values of F and S, multiply them, you get the energy. We got instrument also which measures the energy, right? There are things to measure energy. This is why only we are seeing the energy rating over the food packages, because people can read energy. This is why. But what is efficiency now? The formula of efficiency is efficiency equals useful energy over total energy times 100. This is your efficiency in percentage. What is useful? Useful is 8. Total was 10 joules times 100. What you got? 80%. So your device was 80% efficient.
Yeah.
Okay. That is the thing here. You know, the old yellow bulbs of those days were only 5% efficient. Can you imagine? Only 5% efficient. That means that if your ancestors were putting on, were paying for 100 joules, they were only getting the light for 5 joules. 85%, 85 joules were wasted as heat, as sound. Okay. But okay, you may imagine like we are only 5% efficient, and you may think there is a this was a century ago thing. So we may have become efficient to 95% at least till today. No. So the bulb, the LED bulb which we are having right now, they are only 20% efficient, maybe 50%. The most efficient bulb which we are having right now is only 20% efficient. If we are putting 10 joules as input, we are only getting the light of 20 joules, not 100 joules. 80 joules are a wastage. But as technology is evolving, we are trying to make devices more efficient. This is why efficiency rating is also mentioned over the back of electrical instruments. So when you purchase any of the instrument, read the efficiency rating. Higher the efficiency rating, your electricity like bill will be reduced. Then obviously if you are putting 100 joules and now your bulb is lighting up 20 joules for a day and 80 joules are a wastage, then your same 100 joules, if you are 100% efficient, can light up for 5 days, 20 20 20 20 20. This makes total in 100. So 5 days continuously you can light up the same amount. This is the use case of efficiency. So we are moving towards efficiency, but it's not that easy. We are only in 100 years, or maybe in 50 years, we have only raised from 5% to 15%. A device with the energy efficiency of 30%, 35% is assumed to be very good in efficiency. See, so we are moving, and as we rise on the efficiency of electrical instruments, it will get more tough to make it more efficient. Anyways, another thing is conservation of energy. Conservation of energy. Conservation of energy. Now, conservation of energy tells us that energy can neither be created nor be destroyed. Neither you can create it, neither be created, nor be destroyed. You cannot create it, you cannot destroy it. You can only change its form, you can only transform it. For example, okay, the amount of energy which was there at the time of Big Bang, when the universe was created, the same amount of energy, not a single joule more, not a single joule less, exact the same amount of energy should be there right now in the universe. Okay, so energy can neither be created nor be destroyed. And if you ask us, so how was the energy was created at the very first time, which was there at the time of Big Bang? We don't have the answer, we are still finding it. Okay, but as of today, we don't know how the energy was created. We have never seen it being created or destroyed. So if they ask you, explain the law of conservation of energy, it's a law. So laws are, okay, we don't ask why for the laws. It is, okay, it is from the observation that we see around ourselves. So we don't have the answer for that conservation of energy. Why is it happening? It's a law. We just say it's a law, like Newton's laws. It happens. Law of inertia, it happens. Okay, we don't know why is it happening. So these are the laws. It is one of the law of conservation of energy that will be continued till your graduation if you continue in physics. It says energy can neither be created nor be destroyed. It can only be transferred from one form to another or one position to another. That means the total amount of energy of a system is conserved. That means if universe is a system, doesn't it mean you have not added, created, you have not added in the universe, you have not destroyed from the universe. Whatever amount of energy was there is still inside. That means energy of an isolated system is conserved, is constant. Okay, so there are two ways of defining conservation of energy. First is you can neither create or not destroy the energy. What you can do, you can only transfer energy. That means move energy from one place to another, or transform energy, change the form of energy from one form to another. This is what we can do. Second way of defining law of conservation of energy is energy of an isolated system. For example, my universe is an isolated system. Why isolated? Because as of our knowledge, there is no external effect happening. There is no outer universe. Universe is universe. If you want to create an isolated system, that means if you are having a box, a glass chamber, just make sure the external heat of the air, the humidity, cannot change the temperature inside the box, cannot change the amount, the mass, the energy contained. It cannot change anything inside the box, and the box should be isolated. This is our system. This is what we call as isolated system. So for an isolated system, the energy is conserved. Whatever energy is there, if you're not adding up, if you're not removing it, so energy is constant, is of fixed amount. You cannot create energy, that's for sure. So if somebody tells you that he has discovered a way of infinite energy, there is nothing like infinite energy. Okay, we can only transfer energy from one form to another, and the greatest source of energy that we are having is the sun, because whatever we see around ourselves is everything an outcome from sun. See, if you are having yourself, okay, so we have evolved from cells. Okay, so we are also a byproduct of sunlight. Somehow we are eating food. Food is coming from what? Sunlight. Glucose is made from sunlight. Okay, we are seeing plastic, it's a fossil. We are seeing fuels, it's a fossil. It is coming from plants and decaying matter of the old days, the ancient times. So they were also have fed up over the foods and plants. in the like millions of years back, and those foods and plants are also a byproduct of sunlight. So everything that we see around ourselves is coming from a basic source, sun. So what I'm saying is, you cannot create a new form of energy. We are the ultimate source of energy is sunlight. Okay. So if somebody shows you a perpetual motion machine, it's not in our syllabus. It's just a side quest.
What is a
Perpetual motion machine. So I think every kid in his childhood try to make a perpetual motion machine. At least he thinks of doing so. Perpetual motion machine. Perpetual and motion and machine. That means a machine that works on itself. A machine that moves on itself. No fuel, nothing else.
to make them?
So if you made one, then for example, you created a wheel which rotate on itself. A wheel.
Yeah.
So you can remove the wheel, okay, and then you can add gears in the wheel. You can attach the wheel in your car, and your car can go eternally without the fuel. This is how everyone is chasing the perpetual motion machine. During the time of World War II, people were making the ideas of perpetual motion machine of those days. They were filing the patents for it. Okay.
Okay.
Though nothing can be created like such. It is against the law of conservation of energy. Because in perpetual motion machine, you are moving something eternally, which is not possible on its own. You are moving something on its own. Nothing is on its own. Everything is borrowed. You are borrowing the energy from one to another, right?
Yeah.
Okay, you are not on your. So they never created one. They tried. When you tried something, you can patent your idea into the patent office of your country, right? The idea can be patented. So those scientists were patenting the idea.
I don't understand. So you said it has to be emotional the time, right?
Yeah, motion eternally.
Yeah. So then why can't they just get like a motor?
Why can't they just what?
Get a motor. Like they just.
But motor required now the fuel, the electricity.
Yeah.
But I'm saying something is moving on its own. You want to create something which do not require anything. You just, yeah, something like they were creating, you pedal it once and the wheel will move forever. It's not possible. Okay. Because if you are putting something, your input energy is something, your output energy will exactly be same, and your useful energy will be less than your input energy. I already showed you. Total energy is always greater than useful energy. So if you are pedaling a wheel with using 10 joules of energy, the output, the useness that we want to see in 10 joules of energy will always be less than 10 joules. And we are thinking of making 10 joules into infinity. But it's not even possible. You cannot even make 10 joules equal to 10 joules. It's about making 100% efficiency, and we are near to about 15% efficiency. You can only make 10 joules into 1.5 joules, maybe 2 joules, not even 10 joules. And you're talking about making it infinity. It's not possible. Okay. But at those days, they do not believe the law of conservation of energy. And this is why the patent offices were so fed up with these guys. They banned patenting the perpetual motion machine ideas over those days. And this is why we see nowadays we don't hear about this PMM, because they are banned.
Maybe say that every Australian should do that.
Every Australian, okay, I'm not saying every Australian. I said that every kid in his childhood get an idea of these making something like this, which moves on its own. At least I did. So it happens,
Oh, like, okay, yeah.
but it is not possible.
What is?
Yeah, though I didn't know about perpetual motion machine, I was just in my own mind, we will create something. It doesn't work. We call them such instrument, whatever machine you're trying to build, which work on its own, are collectively known as perpetual motion machine. Perpetual means on its own, by itself. It's not possible.
Yeah.
Okay, so this was all about the conservation of energy. In energy, we are having this much only. Now what is left? The next thing is work. Okay, this is the agenda for the next lecture. That's all for now.
Oh.